You've been asked to write down 3 multiplied by 3. Remember, you haven't been asked to calculate it. So you pick up your pen and write it as 3 times 3. Here we are multiplying 3 by itself just once. Now let's say you've been asked to write down 3 multiplied by 3 multiplied by 3. You write it down as 3 times 3 times 3. In this example, we are multiplying 3 by itself twice. 3 multiplied by itself, multiplied by itself. Now you've been asked to write down 3 multiplied by 3, multiplied by 3, and so on 7 times. So now you're kind of bored, but you don't have a choice. So you write 3 times 3 times 3 times 3, and so on 7 times. Yes, I know what you're thinking. The more number of times you multiply a number by itself, the more tedious it gets for you to write it down. So, that brings us to the question, is there an easier way to denote these kind of operations? What kind of operations am I talking about here? The ones in which a number is multiplied by itself many number of times. The answer to that question is yes, we do. Which brings us to the topic of exponents. 3 multiplied by 3 can be written as 3 with a 2 in the superscript. This is read as 3 raised to 2. How do we get a 2? It depends on the number of 3's you can see. So we have 2 3's here, and hence we write it as 3 raised to 2. In the second case, we can see 3 3's. Hence, it can be written as 3 raised to 3. How do we get a 3 in the superscript? That's because we have 3 3's. And in the final example, we have 1, 2, 3, 4, 5, 6, 7. 7 3's. So we write this long string of numbers of 7 3's as 3 raised to 7. If we have any number, say a, multiplied by itself many times, we write it as a multiplied by a, multiplied by a, multiplied by a, and so on. If there are n number of a's in this product, then it can be written as a raised to n. The number a is called the base and the number n is called the exponent. In the 3 examples we saw, all of them have a base equal to 3. It is just the exponent that varies. In the first case, the exponent was 2. In the second case, the exponent was 3. And in the final example, the exponent was 7. In the coming videos, we will look at the different properties of exponents. Until now, we have worked only with positive exponents. Here's a very simple example to understand negative exponents. Consider this number 3 raised to minus 4. Since we are familiar with positive exponents, let's understand how we can write this negative exponent as a positive exponent. We multiply and divide the number by 3 raised to 4, multiplied by 3 raised to 4 and divided by 3 raised to 4. In short, we are multiplying the number by 1, which will keep the original number unchanged. That equals 3 raised to minus 4 multiplied by 3 raised to 4 divided by 3 raised to 4. We multiplied this with this and divided by this. Focus on the numerator now. Since the base is the same, we can use the product law to write it down as 3 raised to minus 4 plus 4. And we write the denominator as is. Minus 4 plus 4 equals 0. Hence, that would equal 3 raised to 0 divided by 3 raised to 4. And since we know that any non-zero number raised to 0 equals 1, we can write it down as 1 divided by 3 raised to 4. Let me repeat. This is a very important property. Any non-zero number raised to 0 equals 1. This was our original number, 3 raised to minus 4. And we got the answer as 1 divided by 3 raised to 4. So all we did is change the sign of the exponent and wrote it under 1. So we can generalize it as a raised to minus m equals 1 divided by a raised to m, where a is not equal to 0. Because if a is equal to 0, then we would have 0 in the denominator, which would make it indeterminate. This term is read as a raised to negative power m. There's a very simple trick we need to understand here. Consider 3 raised to minus 4. When we have to write it down as a positive exponent, it equals 1 divided by 3 raised to 4. So all we did here is change the sign of the exponent and wrote it under 1. Now consider 21 by 37, the whole raised to minus 7. To write it down as a positive exponent, we write it down as 1 divided by 21 by 37, the whole raised to 7. Again, we just changed the sign of the exponent and wrote it under 1. The same trick can be used for positive exponents too. Now consider 4 raised to 3. We can write it down as 1 divided by 4 raised to minus 3. We changed the sign of the exponent and wrote it under 1. Now that we know how we can find the square of a number, we can try to understand what square roots are. This is a topic which many students find really difficult to understand. So here's a chance to understand this topic well and score better. Consider any number. Say 4. 4 when squared gives us 16. And the square root of 16 gives us 4. Well, that's your concept. Now we shall see how we represent square roots. This is how we would represent the square of 4. 4 raised to 2. 2 is called the power and 4 is the base. Now how do we represent the square root of 4? Well, this is how we write it. This symbol is called the radical or the square root, and the number inside the symbol is called the radicand or the base. That's the first thing we learned, how to represent a square root. But here's a simple way to remember it. We know that 5 squared is 25. This 2, when transposed to the other side, becomes a square root. So we can say that the square root of 25 is 5. Now let's look at something really interesting about the square roots. What's the square root of 16? Yes, it's 4. This means that if we square 4, we will get what is under this radical. Similarly, the square root of 256 is 16. If we square this, we will get this. Now let's try playing with these numbers. Let's try writing 16 in exponential form. We know that 16 can be written as 2 raised to 4. So the square root of 16 can be written as the square root of 2 raised to 4. It's the same thing as the square root of 16. Can it be written in some other way? Yes, it can also be written as square root of 4 raised to 2. We just wrote 16 in 2 different ways, 2 raised to 4 and 4 raised to 2. Now let's try writing the number 4 in different ways. 4 can be written as 2 squared, hence this will equal 2 squared. The number 4 can also be written as 4 raised to 1. Hence this would equal 4 raised to 1. Just look at these things now. What do you observe? What happens to the base and what happens to the exponent? Let's look at the first example. The base remains the same, but the exponent is halved. It's divided by 2. Now let's move on to the next expression. Again, the base remains the same and the exponent is halved. Does this work every time? Let's see. This can be written as square root of 2 raised to 8, or maybe even square root of 4 raised to 4. And 16 can be written as 2 raised to 4 and even 4 raised to 2. In this case, the base remained the same and the exponent was halved. And in this case too, the exponent was halved. So remember, when you have a number in exponential form and you want to find its square root, just keep the base same and halve the exponent. The best way to find the square root of any number is to use a calculator. But if you're asked to find the square root of a number without using a calculator, there are two ways in which we can do it. The first method is phenomenally simple. It's called the prime factorization method. We will look at the second method in the coming videos. If you have watched the previous video, you should be familiar with what square roots are. So we can look at square roots of slightly larger numbers in this video. So we want to find the square root of 225. Our aim is very simple. We have to reduce this number to its prime factors. That's all. How do we do it? Before we go ahead, let us revise what prime numbers are. A prime number is a number which is divisible only by itself and 1. Say 5. 5 is divisible by 1 and it's divisible by 5. There's no other number which can divide 5. 1 and itself. Hence, it's a prime number. Let's consider 8. 8 is divisible by 1, 2, 4 and 8. Apart from 1 and itself, it's also divisible by 2 and 4. Hence, it's not a prime number. So let us start reducing the number 225 into prime factors. Prime factors are the factors of this number which are prime. We can write 225 as 5 multiplied by 45. 5 is prime, but 45 isn't. So let's reduce 45 further and write 225 as 5 times 5 times 9. We wrote 45 as 5 times 9. 5 is a prime factor, but 9 isn't. 9 can be written as 3 times 3. Hence, 225 can be written as 5 times 5 times 3 times 3. In this way, we reduce 225 into its prime factors. This was simple, but is it the quickest way? No. Let's look at a quicker way. We write 225 like this and draw two lines here, like this. 225 is divisible by 5, so we write a 5 here. We just write the prime factors in this column. 5 multiplied by 45 gives us 225. 45 is not prime. Hence, we continue with this process. 45 is also divisible by 5. Hence, we write a 5 here. And 5 multiplied by 9 gives us 45. 9 is not prime, and we can say that 3 multiplied by 3 equals 9. That's where we stop, when we get a prime factor here. So if we look carefully, we have got all the prime factors. 5 times 5 times 3 times 3. Why do I say this method is faster? Look at the first 5 in this method. We continue to write it every step. Then we repeat the 5 times 5 we got in this step in the third step. Many of the numbers are repeated in every step, and hence there's a bit of a redundancy. If you really want to know how tedious this method can get, try reducing 216 into its prime factors. By now, we should be fairly comfortable with prime factorization. But now we're getting to the most important point. How will this help us find the square root of 225? You will not believe how simple it is. We write this as square root of 5 times 5 times 3 times 3. We have to make groups of two same numbers. This can be our first group, 5 and 5. We can make another group, 3 and 3. We basically formed pairs of same numbers. So we have two pairs of same numbers here, 5 and 5 and 3 and 3. Once we form pairs, to find the square root, all we have to do is pick one number from each pair and multiply them. So from the first pair, we pick 5, and from the second pair, we pick 3. And we multiply 5 and 3, which gives us 15. At first, this seems long, but with practice, it gets very simple. Hence, we can say that the square root of 225 is 15. All we did is broke down the number to its prime factors, made pairs, chose one number from each pair, and multiplied them. In the next part of this video, we will see how we can find the square root of 11,025 using this method. Hence, our aim would be to reduce 11,025 into its prime factors. So we write 11,025 here and draw two lines like this. If we know the rules of divisibility well, we can say that this number is divisible by 3, 5 and 7. So we can start with any prime number. Say 5. So 5 multiplied by 2,205 gives us 11,025. This number again is divisible by 5. Hence, we write a 5 here. And 5 multiplied by 441 gives us 2,205. Of course, you would take a bit more time to find the numbers here, but that's perfectly alright. And remember, we keep just the prime factors on the left-hand side. Now, since 441 is divisible by 3, let us write 3 here. And 3 multiplied by 147 gives us 441. This number is also divisible by 3. And 3 multiplied by 49 equals 147. And the only prime number 49 is divisible by is 7. And 7 multiplied by 7 is 49. And yes, we stop here since 7 is a prime number. So 11,025 can be written as 5 times 5 times 3 times 3 times 7 times 7. Hence, the square root of 11,025 can be written as square root of 5 times 5 times 3 times 3 times 7 times 7. The next step is to make pairs of the same numbers. And after we find the pairs, we choose one number from each pair. So we have 3 pairs here, a pair of 5s, a pair of 3s, and a pair of 7s. We choose one number from each pair. So from the first pair, we choose 5. From the second pair, we choose 3, and from the third pair, we choose a 7. And to find the square root, all we have to do is multiply these numbers. 5 multiplied by 3 multiplied by 7 equals 105. Hence, the square root of 11,025 is 105. This part of the problem where we choose one number from each pair is really simple. What we really need to be good at is finding out the prime factors quickly. The video on cubes is very similar to the one on squares. If you've understood the concept of squares, the concept of cubes will be stress-free. Let us get to the basics first. Look at this number on the board. It is read as 7 raised to 3. And raised to 3 is called cubed. So the number can be called 7 cubed. Why do we have a distinct name for raised to 3? Well, it's the same reason as to why we have a distinct name for raised to 2. It's because raised to 3 has many applications. Here is one of the practical examples. Assume we have a box in the shape of a cube. Assume the lengths of all its edges equal 3 centimeters. If we remember correctly, the volume of a cube is given by side multiplied by side multiplied by side. So that will equal 3 multiplied by 3 multiplied by 3. So this is actually 3 cubed. That will give us 27. So that's one of the practical applications of cubed or raised to 3. But wait, are we forgetting something? Yes, it's the units of the answer. So the units of each side are also multiplied to get centimeters cubed. That's the precise answer. The volume of the cube is 27 centimeters cubed. The answer can also be written as 27 cubic centimeters. So we can see that when 3 lengths are multiplied, we utilize the concept of cubes. Let's understand another straightforward example. Solve 10 centimeters multiplied by 9 centimeters multiplied by 6 centimeters. Multiplying the lengths gives us 540. We did not use the concept of cubes here as we have three different numbers. But multiplying the units gives us centimeters cubed. So the answer can also be written as 540 cubic centimeters. So whether it's squared or cubed, the units also differ accordingly. Now there's a vital property we need to understand. To understand the property, here are a few examples. How do we find the value of 7 cubed? It is 7 multiplied by 7 multiplied by 7, and that equals 343. Minus 14, the whole cubed, equals minus 14 multiplied by minus 14 multiplied by minus 14. That equals minus 2744. And similarly, 18 cubed equals 18 multiplied by 18 multiplied by 18, which equals 5832. Observe the sign of the number and the sign of the answer. If negative, then negative. If positive, then positive. So we can say that for cubes of numbers, the sign of the answer is same as the sign of the number. That is, cube of a negative number will result in a negative number, and the cube of a positive number will result in a positive number. Now, all of us know how to find the cube of a number. So 3 when cubed gives us 27. It means 3 multiplied by 3 multiplied by 3 equals 27. So what is a cube root? Well, the cube root of 27 is 3. That's all. This is the most important concept of cube roots. The rest of the video will just focus on how cube roots are denoted and its application. So remember, 3 cubed is 27 and cube root of 27 is 3. Well, this is how the symbol of a cube root looks like. A root sign with a 3 here. So we can say that the cube root of 27 is 3. And as we saw in the square root video, this root sign is called the radical. And the number inside it is called the radicand or the base. Here's a better way to understand the concept of cubes. 4 cubed equals 4 times 4 times 4, which equals 64. We all know this. This 3, when taken to the other side, becomes cube root. Hence, we can say that the cube root of 64 equals 4. Now, we're on our way to understand a very interesting concept. We will try to understand this concept with just one example. We know that cube root of 64 is 4. This example looks very simple, but modifying it slightly can make it interesting. Let's play with these numbers. We can write 64 as 2 raised to 6. Hence, cube root of 64 can be written as cube root of 2 raised to 6. We can also write 64 as 4 cubed. Hence, we write this as cube root of 4 cubed. Now let's try writing 4 in an exponential form. 4 can be written as 2 squared. Hence, this would equal 2 squared. And of course, it can also be written as 4 raised to 1. What do we observe? Yes, when we take a cube root of a number in exponential form, the base remains the same and the exponent is divided by 3. 6 became 2 and 3 became 1. Remember, when we take a cube root of a number in exponential form, we should keep the base same and divide the exponent by 3. Let's quickly look at a couple of examples. Say we want to find the cube root of 4 raised to 9. The base actually equals 262,144. Imagine finding the cube root of this big number. But using our technique, all we need to do is keep the base same and divide the exponent by 3. Here the base is 4. Hence we write a 4 here. And divide 9 by 3. Hence we get the cube root of 4 raised to 9 as 4 raised to 3. Now let's try finding the cube root of 7 raised to 6. We can write it as 7 raised to 6 by 3, which equals 7 raised to 2. So remember, keep the base same and divide the exponent by 3. In the coming videos, we will see how we can calculate the cube root of large numbers which are not in exponential form. In the previous video, we learned how we can find the cube roots of numbers in exponential form. But what if the numbers are large and are not in exponential form? Well, we use the prime factorization method. Say we want to find the cube root of 216. Our aim is to reduce this number to its prime factors. We write the number here and draw lines like these. Now we think of one prime number that is a factor of 216. We know that 2 is a factor of 216, so we write a 2 here and we divide 216 by 2 and write the quotient here, that is 108. 2 multiplied by 108 gives us 216. So we continue with the same procedure. We think of a prime factor that is a factor of 108. Well, 108 is also divisible by 2, and 2 multiplied by 54 gives us 108. Again, since 2 is a factor of 54, we write 2 here and write 27 here as 2 multiplied by 27 equals 54. We stop when we get a prime number here. 27 is not a prime number, and hence we continue with the same process. Now the prime number that is a factor of 27 is 3. So we write 3 here. 3 multiplied by 9 equals 27. And we know that 9 equals 3 multiplied by 3. This is where we stop. We stop when we see a prime number here. So we have reduced 216 into its prime factors. 216 will equal the product of all these numbers. We can write cube root of 216 as cube root of 2 multiplied by 2 multiplied by 2 multiplied by 3 multiplied by 3 multiplied by 3. Remember, do not forget to include the prime number which is left at the bottom. So what do we do now? If you remember correctly, in squares, we made pairs of same numbers and chose one from each group. In cubes, we make groups of 3 same numbers and again choose one from each group. Hence, to find cube root of 216, we group the 3 2's together and the 3 3's together. And from each group, we pick just one number and multiply them. So from the first group, we pick 2, and from the second group, we pick 3. And after we multiply them, we get 6. Hence the cube root of 216 equals 6. So now we know that once we reduce the numbers to its prime factors, the task is very simple. We make groups of 3 and choose one number from each group and multiply them. And it's a good idea to memorize the cubes of numbers from 1 to 10. I'm talking about the cubes and not the cube roots. Why do I say this? It's because you'll be able to find the cube roots of large numbers in a matter of few seconds, maybe even 5 seconds. And when I say large, I mean numbers up to even 6 digits long. We will see that in coming videos. Assume we want to find the cube root of 2197. Now to get the answer in 5 seconds, there are 2 things you need to know. First, we need to know the cubes of numbers from 1 to 10 by heart. Here's the tables of cubes of numbers from 1 to 10. In the first column, we have the numbers, and in the second column, we have the cubes of those numbers. 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, and so on. Second, we should know that for 4, 5, and 6 digit numbers, their cube roots will always be 2 digits long. Since 2197 has 4 digits, its cube root will also be 2 digits long. That's it. Only these 2 things. Cubes of numbers from 1 to 10 and the fact that large numbers which are 4, 5 or 6 digits long will have cube roots which are exactly 2 digits long. So let's move on. Look at this table for a moment and think. Is there anything that stands out? Pause the video and think for a moment. This is what you should have observed. Look at all the units digits of the numbers in the cubes column. They are all different from each other. All numbers from 0 to 9 are covered. 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. Knowing this fact will help you understand the first step in our method. Okay, now we're all set to go. The first step of our method is to look at the units digit of the number. The units digit of 2197 is 7. So we look at our table. In the cubes column, we look for a number which has its units digit as 7. It's this one, 27. So we take the number from the first column corresponding to it and write it in the units place of the answer. The number corresponding to 27 is 3. So we write 3 here. So the first step directly gave us the units digit of the answer. Remember, the answer is the cube root of 2197. The next step is interesting. We ignore 3 digits from the right of the number. So we ignore 197 for the moment and look at the number that remains. It's 2. This number is very crucial. We check where 2 is placed in the cubes column. That is, we check the position of the remaining numbers in the cubes column. In the cubes column, the number 2 lies between 1 and 8, between these two numbers. That means it is placed between 1 cubed and 2 cubed. We basically looked at the corresponding number column. The last step is very important. Now that we know where it is placed, we choose the lower number in the corresponding number column. The lower of 1 and 2 is 1. That's it. This is your tens digit. So cube root of 2197 is 13. Remember, we always choose numbers from the first column, which is the numbers column, to write the digits of our answer. 3 was chosen from here and 1 was chosen from here. This looks really long at the first look, but with practice, trust me, you'll be able to solve it in 5 seconds. Now let's solve another problem so that you understand better. Say we want to find the cube root of 195112. This number is 6 digits long and hence its cube root will be 2 digits long. Remember, cube roots of large numbers which have 4, 5 or 6 digits will always be 2 digits long. Now let's see the units digit of the number. It's 2. In the cubes column, we look for a number which has its units digit 2. Yes, it's 512. And the corresponding number in the numbers column is 8. So we write a 8 in the units place of the answer. Now we ignore 3 digits from the right, that is 112, and what remains is 195. Now where is 195 placed in the cubes column of the table? It is placed between 125 and 216. That is, it is placed between 5 cubed and 6 cubed. So from the numbers column, we choose the lower number among 5 and 6. It is 5. And we write this number in the tens place of the answer. Hence, the cube root of 195,112 is 58. With good practice, you will be able to solve this in 5 seconds. And remember that this method is a shortcut and cannot be used to solve questions in your exams. You may use this method purely to verify your answers.